Hello guys, it's me Sir Ernest, and today we're going to talk about forces that depend on position. So for example, when you have a spring like this, and then let's say this spring is stretched, and stretched. You will notice that when you stretch the spring like this, you will feel that it becomes harder to do the stretching or compressing as the spring becomes more deformed. So this is because of the reaction of the spring, wherein the reaction of the spring by Newton's third law, like this, becomes larger as you increase the deformation, or as you apply more force on the object, the amount of deformation increases. So this force, the spring force, as well as the applied force on the spring, are examples of position of the forces that depend on position. So we usually write this as F, which is a function of position. When you say position in this context, that the amount of deformation that the spring have undergone. So other examples of forces that depend on position is your electrostatic force, wherein if you have, let's say, two charges, say Q1 and Q2, and the distance between them is R. So the force exerted on Q1 by Q2 or on Q2 by Q1 is given by this equation. This is equal to 1 over 4 pi epsilon sub 0 times Q1 Q2 over R squared R hat. So as you will notice that as the charges move further away from each other, the magnitude of the force that they exert on each other decreases by 1 over R squared. So this is an example of a force that varies with position. Gravitational force, on the other hand, or similarly, gravitational force, or the universal law of gravitation, is also of the same form as this Coulomb's law. So, using that in one dimension, okay, so in one dimension, let's say along X, the force would be along X, which is a function of X. So Newton's second law of motion in this dimension will now be written as F as a function of X is equal to m x double dot, where m is the mass of your particle and x double dot is the acceleration along the x direction. So we notice that by chain rule, we can rewrite x double dot as, which is defined as the derivative of your velocity with respect to time, and by chain rule, this is now equal to derivative of x dot with respect to x times derivative of x with respect to time. So we know that derivative of x with respect to time is just x dot. So this becomes x dot derivative of x dot with respect to x, or v times derivative of v with respect to x. So from here, we can substitute this in our equation of motion. So this becomes f as a function of x is now equal to m x dot times derivative of x dot with respect to x. So if we're going to do some mathematical manipulation here, we can actually rewrite this product when you, let's say, you want to reverse. Okay, so let's say you want to reverse the you want to reverse the derivative here. So we're actually doing putting the x dot inside the derivative again. So this is actually equal to m times derivative with respect to x of x dot squared over 2. Okay, which since m is a constant, we can put this inside the derivative as well. So this becomes derivative with respect to x of m x dot squared over 2. And you can see that this is familiar to you, and here we're going to define this as your kinetic energy. Okay, so here we define our kinetic energy T. So in our class today, we're going to represent kinetic energy as capital T. Okay, we're going to reserve capital K in a different lesson, which we're going to know later on. So here, the kinetic energy will now be equal to 1/2 mx dot squared, or simply 1/2 m v squared. Okay, so from here, we can rewrite the equation of motion as f, so function of x, will be equal to the derivative of the kinetic energy with respect to x. Okay, so that's it. That's a simple introduction to forces that depend on position. In the next video, we're going to relate this result to the work done on an object as it undergoes displacement caused by a net force. Okay, so but for now, thank you guys for watching. I hope you learned something today, and I'll see you guys in the next video. Bye bye.